I'm carrying on with this light thing. Right, what is refraction? Refraction is the change in direction of waves at a boundary. Refractive index is calculated as sine I over sine R. And what is the refractive index? Index is how much material bends light. Right, so let me get the mouse. The ray of light coming in is the incident ray. The line perpendicular to the boundary is the normal, and you measure the ray of incident ray or angle of incidence, sorry, to the normal. So that there is the angle of incidence. That ray is refracted. That is the angle of refraction. It's measured to the normal. The normal's here. It's at right angles to the boundary. And it's called the refracted ray. Right, there's one more thing, which is this one. It's good to know this as well, actually. This is from the book. It's the Pearson book. So that's what we're using at the moment, the Pearson book. Right. So you've got radio wave, microwave, infrared, visible light is in the middle. Then you've got, so remember, infrared and then ultraviolet, X-rays and gamma rays. Radio waves I know have long wavelengths, they have short wavelengths. And then you've got Roig Biv. The white light splits up into that Roig Biv. Roig Biv. Roy G. Biv, or however you want to say it. Right, so remember radio waves, microwaves, infrared, light, ultraviolet, X-ray, and gamma. Right, let's carry on then. So this question is about parts of the electromagnetic spectrum. Right, so remember you said radio, infrared, visible, ultraviolet. You've got X-ray, and is this microwaves? Let's have a look. Let's make it smaller. Let us put it here. Yeah, radio, micro, infrared, visible light is here, ultraviolet, X-rays, and gamma rays. Okay, that's good. Right, the two parts, so it's micro and X-rays. Okay, the sun emits different types of electromagnetic waves. Which of these is the same for all the waves? The speed is always the same. The speed does not change. Which type of electromagnetic waves causes sunburn and snow blindness? It will be UV. Ultraviolet. If you're in the sun for too long, it can burn you. But I think it's about 20 minutes or half an hour exposure on your skin is good because it produces vitamin D. Okay, let's keep going. Question number 3. Diagram shows a ray of light passing through a semicircular block. Have you noticed it's gone that way and it's reflected back? Yeah. Dotted line is the normal, so this line is a normal. That's called the normal, and it's at right angles to the boundary. The process shown in the diagram, because it's totally internally reflected, is total internal reflection, TIR. Okay, what is the angle labeled theta? Angle of reflection. Angle of reflection. So okay, right. The diagram shows another light ray entering a right angle glass block. It hits the surface inside. So now basically what we do, we know what they said, 45 degrees. At 45 degrees, you're going to get total internal reflection. So what's going to happen is this is going to bounce. It's going to go here at 45 degrees. Then you've got the normal. And then it's going to bounce back and go that way. So you're going to get it taking this path. You're going to do that with a ruler. There you go. Right, okay. So now this question about sound waves. Sound waves are what type of waves? They're not transverse waves, they're longitudinal waves. Are they transverse waves? Are they, where are we? Sound waves are, they're not that. No, it's one of these two. They are longitudinal waves, so it's this one here. Right, let's quickly discuss longitudinal and transverse. So longitudinal waves, right? They travel along the direction of vibration. Right, let me look. Let me look at a better definition. Longitudinal, where are we? HIJK. Right, okay. Vibrations of these waves are along the direction in which the wave travels. Right, so what I'm going to do is I'm going to write that. You know what I'm going to do is I'm going to write it up there. Because that's always useful to have in our heads. So number 5, number 6. Longitudinal waves. Right, we need to get this right. Longitudinal waves. The vibrations of these waves are along the direction in which the wave travels. Right, and a transverse wave. Transverse waves. The vibrations of these waves are at right angles of perpendicular to the direction of travel. Okay, I just wanted to do that. It's good to know that actually. Okay, so let's quickly describe an experiment to measure the speed of sound in air. There's a few points. Right, first of all, right, two people stand 100 meters apart. Right, that's the known distance. Right, 100 meters is a good distance. 100 meters apart, measured using a tape measure. Right, then what happens is the first person makes a noise. The second person starts a stopwatch as soon as they see the first person clap or make the noise. Right. As soon as the second person so remember the first one is seeing the noise being made, and then when the second person is seeing the noise made, and when the second person hears the noise, they stop the stopwatch. Repeat, remove anomalies, and average out the results. Yeah. Use the formula speed equals distance divided by time to calculate the speed. So this is just one way of doing it. There's lots of other ways. Right, so first of all, you've got the distance, sensible distance. You've used a tape measure. The second person makes a noise. The first person makes a noise. The second person will see it, and when they hear it, they will stop. So they'll start the stopwatch, and then they'll stop the stopwatch. You always repeat experiments, and then in this case we're going to use the formula speed is distance over time to calculate the speed. So we've put everything in. You can also stand 50 meters away from a wall, and when you hear the echo, you can then use that as a way of stopping the stopwatch. Right. Oh, there's some more here. Right, the speed of sound in air is different for different heights. So the further up you are, the slower the speed of sound. So what we do is we want to estimate that at 6,000. Get a ruler, go across, down to there. So it's 310, 316. So it's 316 meters per second. Describe the pattern. We can say as the speed of sound, right? Okay, yeah. As the speed of sound increases, as the what's the best way to say it? Speed of sound decreases with height, and it is a linear relationship. Yeah. Okay, let me write that down. Speed of sound decreases with height. Did I write height like that? I can't believe I did that. Height. It is a linear, as in straight line relationship. Linear relationship. There you go. Yeah, when's this gonna end? Right, okay, last bit. Two marker. Some airplanes travel faster than the speed of light. When an airplane travels, it sends a shock wave called a sonic boom. It's easy for an airplane to make a sonic boom when it travels higher up. Yes, that is true. Why? Because the aeroplane does not have to travel as fast to reach the speed of sound. There you go. Right, call it quits there. We'll come back to it.